Good evening, everyone. Welcome to the 8th problem solving session of the Computational Continuum Mechanics course. As you know, I'm Naresh. I'm a research scholar in the Department of Civil Engineering at the Indian Institute of Science. So today we'll continue with wherever we left off in the last session, which is objectivity and stress rates. Just a minute. So in the last session, we were looking at the requirement of work conjugacy for between the stress strain quantities. So we saw what. So we looked at the ideas of stress, the balance laws, and then we looked at the principle of virtual work, which is equivalent to the equilibrium equations. Then, based on the principle of virtual work, we defined what is work conjugacy. So I can put them together here. So let me quickly recap, and I'll also put together what we'll be seeing today. So in the last session, we started off with the idea of stress. And we saw what is the Cauchy stress. Then we looked at balance laws, rather equilibrium. And we saw that for the translational equilibrium is the divergence of sigma is equal to 0. Sorry, divergence of sigma plus the body force intensity is equal to 0. And for rotational, this is the translational equilibrium. And for rotational equilibrium, the idea was the stress tensor, the Cauchy stress tensor is symmetric. Then we looked at the concept of principle of virtual work. And we said that it is, we showed that it is exactly equivalent to the equilibrium equations. So principle of virtual work. What does it say? It says that the virtual work done by the tractions and the body forces this is integrated over the volume, is equal to the stress power or the virtual stress power actually. So this is equal to the Cauchy stress times the contraction of Cauchy stress with the virtual rate of deformation tensor. So we looked at this expression, which says that the virtual work done by the tractions and body forces on an admissible virtual velocity field is equal to the this integral of this is equal to the so this is the external virtual work done. This is the external virtual work done, and we said this has to be equal to the internal virtual work done, and the internal virtual work done is nothing but the contraction of the Cauchy stress with the rate of deformation tensor. And then we also, so this is a purely spatial description. We also saw the material descriptions of this. The material descriptions of this statement. So in the process, we said that we can say dV is equal to J dV, no? Therefore, we can define a certain stress called the Kirchhoff stress, which is J times sigma. So this is Kirchhoff stress. So here we define the concept of work conjugacy. Work conjugacy. That a certain stress measure T and a certain strain measure, say some epsilon, they are said to be work conjugate to each other if we can express the virtual internal work as integral T contracted with the del of epsilon integrated over the volume. So this is work conjugacy with respect to the undeformed volume. And we can also have a work conjugacy with respect to deformed volume. So with respect to V naught, the undeformed volume, one work conjugate pair is that of the Cauchy stress and the rate of deformation tensor. So these are work conjugate. Sorry, this is not undeformed. This is with respect to deformed volume. Sorry. So the Cauchy stresses work conjugate to the rate of deformation tensor and the velocity gradient tensor with respect to the current deformed volume. And with respect to the undeformed volume, V naught, we have other measures that are work conjugate. So the first one is the Kirchhoff stress and the rate of deformation tensor. These are work conjugate with respect to the current deformed. These are work conjugate with respect to the undeformed volume. And then we looked at another stress measure, which is the Piola-Kirchhoff stress. First Piola-Kirchhoff stress tensor P. That is work conjugate to the rate of the deformation gradient, the material time derivative of the deformation gradient F dot. And the third work conjugate pair that we saw is that of the second Piola-Kirchhoff stress tensor with the material time derivative of the green Lagrange string. We also looked at other measures in the exercises. One was the Hill. What is it? Let me just open that. Yeah. The other work conjugate measure is these two, which is this quantity CSC, sigma defined as CSC. That is work conjugate to minus B transpose, minus B dot. Minus C inverse dot. So this is another work conjugate pair. Then in the next exercise, we saw that the stress tensor defined as pi, which is PC, is work conjugate to minus F inverse transpose dot. So this is another PC is work conjugate to minus F inverse transpose dot. Then we also saw another pair, which is the Hill strain tensor, which is work conjugate to U dot. Just checking where it is. Yeah. Yeah, the sixth one and the final one is the Biot stress tensor, which is defined as half SU plus US, and this is work conjugate to U dot. So these are some 6 work conjugate pairs that we saw last time. Now, what is the next step? So we have identified work conjugate pairs. So we need to relate a quantity with its work conjugate. So we need to relate a quantity with its work conjugate pair to arrive at a constitutive relation. So this is our goal. So this is the constitutive relation. And why do we need constitutive relations? Why do we need constitutive relations? We look at it. So the constitutive relationship essentially gives closure, right? It gives the closure conditions. So we have 5 balance laws, which are so the first one is translation. First one is probably the conservation of mass. In a Lagrangian setting, it is rho J is equal to rho naught. So rho is equal to J rho naught. So it is actually rho dV is equal to rho naught dV naught. This is the conservation of mass. So dV by dV naught is nothing but J. So rho J is equal to rho naught. This is first law. This is the conservation of mass. Then we have the balance of linear momentum or translational equilibrium, which says L dot sigma plus B is equal to 0. B or F. It's actually F per unit mass, per unit volume. Then we have the energy, conservation of energy. So this we have this has not been done in detail, but we have a law of conservation of energy. Then we have angular momentum, the conservation of angular momentum, or the rotational equilibrium, which says sigma is equal to sigma transpose. And finally, we have the second law. So the second law is actually an inequality. We'll also see what it is. So that it is an inequality. So we essentially have, so the conservation, so for a purely mechanical system, we don't really, yeah. So the first law relates quantities such as, so it relates the work done to, let me just write it down from the lecture. So in the lecture notes, you can see the first law states that the stress power sigma in a product, double dot product with D plus rho R minus the divergence of Q is equal to rho U dot. So U is the rate of, U is the internal energy density, Q is the heat flux, R is the heat generation, and sigma double dot D is the stress power. So for a purely mechanical system, let us discount the heat contributions of the heat terms, right? So you can drop these two terms, rho R and del dot Q. So so the number of equations we have to solve for are, the first one is one scalar equation. So this, let me use a different color. The first one is one scalar equation. The second one is one vector equation, which is equivalent to three scalar equations. And the third one is a scalar equation. And if you list the number of unknowns, if you see what the unknowns are, yeah. What's wrong with the pen? So if you see the unknowns, one unknown is we have rho from the first equation. Then we have sigma. We have U. So U is the internal energy. Sigma is the stress. It has got 6 components. Sigma 1, 1. So it is symmetric. So if you consider, if you absorb 4 into 1, we have 6 components up to sigma 1. And rho. So we have got 1, 2, 1, 6, so 7 plus 1, 8. We have 8 unknowns. So these are purely mechanical. For a purely mechanical system, we have got 8 unknowns. And how many equations? We have only 1 plus 3 plus 1, which is 5 scalar equations. So sorry. So let us list the unknowns. Or rather, let's list everything appear in the equation. So it is, we have a rho, we have a j, we have rho naught, and then we have sigma. The body force is specified, so that's not an unknown. And then D and U. So this is not the displacement, this is internal energy density. This is the velocity, the symmetric part of velocity gradient. This is the Cauchy stress. This is the initial density. So this is the initial referential density. This you can say it is known. So this is not an unknown. J is the uh, J is the Jacobian of the deformation gradient. So it is dit of F. And rho is a field variable. So it's a density. Now, if you look at kinematic quantities such as J and D, they can be directly computed from, if given X, given the deformation field X, which is some chi of X T, we can compute J as determinant of grad deformation gradient and D as the spatial gradient of the velocity field. So these two can be directly computed from these. So we can, instead of taking J and D as independent unknowns, you can say X is an unknown. So X is an unknown, rho is an unknown, it is a field variable, sigma is an unknown, and the internal energy U is an unknown. So this has got 3 components. This is a scalar. This has got 6 components. If you consider symmetry, this has got 1. So we have in total 11 unknowns. But how many equations? Equations are just, so one is conservation of mass, conservation of linear momentum, which is like 3 equations. So this is linear momentum. And we have first law. So we have about 5 scalar equations. So we need 11 minus 5, 6 additional equations. For a purely mechanical problem, for a mechanical problem. And the constitutive relations give the closure. Constitutive relations give the closure conditions. So you have a system of equations, but we have fewer equations than the number of unknowns. So it is not possible to solve for all of them. Therefore, we need some conditions called the closure conditions, which close the system of equations. And what closes the system of equations are constitutive relations. And these constitutive relations are determined experimentally. So the only way you can determine them is they are determined experimentally. Yeah, so this is basically the idea. So here, this is incorrect. You don't have 8 unknowns because J, D are also parts of the solution. They are also unknown. So we have about 11 unknowns. It's not 8 unknowns. So let me, so whatever is done on the second page is fine. So we have 5 scalar equations and 11 unknowns. Fine. So since the constitutive relations give closure, they are expected to satisfy certain constraints. So we'll see what they are. Where it is. Yeah, so one thing is constitutive relations have to be between work conjugate quantities. So it doesn't have to be always, but it helps when constitutive relations between work conjugate quantities. So work conjugate quantities often appear in the constitutive relation. So a related concept is that of objectivity, right? So we will see what objectivity is. So consider a body in the undeformed configuration, say B0, and it undergoes a certain deformation and becomes B at time t. So if you look at an elemental, if you look at an infinitesimal vector, it is initially dx, and under the action of the deformation gradient, it takes another form, d small x. Now over and above this, you can superimpose another rigid body motion. So this is the deformation field. Say you have phi. Over and above this, you can superimpose another rigid body motion, say r, or rather q. And the body just rotates, because under rigid body motion, it cannot develop any strain. So the body just rotates and you have another vector dx dot. Dx tilde. Right? So the idea is that you look at the concept of frame of reference. So the frame of reference, as you know from physics, basic physics, is the background against which observations are made. A frame of reference is the background against which observations are made. Right? So let us, yes. So for an example, you can say, suppose you're sitting in a car. So there is a car, and there's a certain bird that is flying here. So the bird, say it is flying at a speed of v1, and the car is moving at a speed of v2, and there's a stationary observer standing outside, and he's observing the bird. He's observing a bird. So he is making observations against the background of stationary objects that are stationary with respect to him, right? So an observer on the road who is not moving with respect to the road will make observations of things moving around him with respect to the background that is relatively at rest with respect to him. So he will make observations of the bird against a tree at a rest, or say at so there may be a house here. So these things are at rest with respect to him, and he is observing the velocity of the velocity of the bird with respect to things that are at rest with him. So his frame of reference is the road's frame of reference or the tree's frame of reference. So let's call this observer O1. And in his frame of reference, the car is moving with a velocity of v2. So let us suppose there's an observer inside the car, and he is also observing the same bird. So the observer inside the car will make observations not with respect to a moving. So the observer in the car will observe that the houses and trees are moving backwards at certain velocity, which is v2, and his frame of reference will be things that are at rest with respect to his position. So for him, the car window is at rest. The components of the car are at rest. From his point of view, anything that is inside the car is at rest for him. Anything that is fixed to the car is at rest. So the background against which observer O2, who is moving in a car, makes observations is the car's frame of reference. So let us say observer O2 is observing the velocity of the bird. So since the observer O2 is moving with respect to the observer O1, observer O2 has to record the velocity of the bird as v1 minus v2, right? So this is the velocity observed by the observer O2. whereas the velocity observed by the observer O1 is just v1. So you see that the velocity of a body, of a particle, is not objective. Different observers in different frames of reference report different values of the velocity. So this can be formalized as follows. Let us say you have a deformation field, you have a motion. Say you have a motion described by x, right? X equal to phi of x comma t is a motion. This is a motion of a body, certain body. Can be rigid, it can involve strains. That's not important right now. And then you say you're suppose you have an observer moving at a velocity c with respect to this observer and rotating at a fixed rate of q, right? Q with respect to. So this is by observer O1. And in the frame of reference of the observer O1, there is another observer O2 who is at a slightly different origin, say C, and he's in a rotated configuration. So you have an observer O1 whose frames are like this. This is O1. And you have an observer O2. He is looking at the same phenomena at a different from a different origin and from a rotated frame of reference. So this is observer O2. And the frames of reference are related by a rigid rotation plus a translation, which is q of t plus q of t x plus c. Now, if you look at the velocity, say v star. V star is what? Just take the material time derivative on both sides. It is c dot of t plus q dot t x. So x depends on time, remember, plus q of t x dot. So it is nothing but c dot t plus q dot x. So let me drop this t dependent. So it is c dot plus q dot x plus q. X dot is nothing but v. Now, if you look at infinitesimal lengths, if you say dx star is nothing but it is the spatial. It's a small. So it is just, let me write it down. It is just f dx, right? So, and f is nothing but the spatial gradient of the deformation field. So we'll see what dx star is. You know, it is, if it is dx is nothing but f dx, and f is nothing but the spatial gradient of the deformation field. So it is with respect to x dx, right? Now let us look at the gradient of the deformation field as observed by observer O2. So this is as per observer O1. And if you look at f star, or the gradient of the deformation field as observed by the observer O2, it will be gradient of x star. But what is x star? It is the gradient of c plus qx. So c is a function only of time, q is a function only of time. They do not have a spatial dependence. Therefore, this c will give us zero tensor, and q remains a constant. So you get a q outside. Plus you have, so this gradient operator will act only on the x. So it is nothing but q times f. So what we see is that f star is equal to qf, which means the gradient operator. So gradient of x star is nothing but qf Therefore, dx star is equal to qf dx, dx capital X. But what is f capital dx? This is nothing but q, this is nothing but dx. So we have a relationship which is dx star is equal to q dx. So this is the law of so this is the way in which, sorry. So if you see what is special about this, so q is a function only of time. It doesn't depend on the spatial location. Dx star and dx are infinitesimal vectors as observed by the two observers. So dx is what the observer O1 says, and dx star is what observer O2 measures. Note that it is not the frame of reference. Note, sorry, it's not the coordinate. Note, it is not a coordinate transformation. That is because both the observers can use any coordinate system to make the measurements. It doesn't matter. They are aware that they have infinitely many coordinate systems against which they can use to make measurements. But the background against which they make the measurements, that they don't have any choice. So they can make measurements only with respect to a frame of reference that they have. But in that frame of reference, they can use any coordinate system. For example, if I'm making, so if this observer has to measure the velocity of something, he has to measure the velocity of a bird against a tree that is at rest with respect to him, and he has to call it a vector v. But this vector v, he can choose to express it as, say, v1 e1 plus 0 e2. Suppose the bird is flying horizontally, plus then it has no vertical component, right? Suppose this is one this is one coordinate system which he can use to make measurements, but the reported values are vectors which do not depend on the coordinate systems. So the observation itself is a vector. They are mathematical quantities that are not dependent on the coordinate system, but he uses a coordinate system to make the measurements. But the measurements are made against a background, which is the frame of reference. So what I would like to emphasize here is that a frame of reference is not the same as coordinate system. So frame of reference is the background against which we are making measurements, for which there is no choice for a given observer. But in that frame of reference, we can use any coordinate system. For example, this observer can choose to use a coordinate system, say 1 dash 2 dash, which is tilted. So in that coordinate system, the same vector will have components v1 prime e1 prime plus v2 prime e2 prime. So that's not a problem. We can choose, but the net vector is actually the same. However, if there is another observer who is rotated or who is spinning with respect to something else, he will not report the same velocity. The velocity vector itself will be different, not just its components in that. So what is special about this transformation? Under an imposed rigid body motion Q, vectors that transform according to this law preserve the inner products and lengths. So this transformation preserves length of the vector and also angle between two different vectors. So how does it preserve the length? Let us say dx, the length of dx star square is nothing but length of q dx squared, and length of this is the inner product. It is q dx dot q dx. And if you remember the definition of transpose, you can take this to the other side with the transpose. So you get dx dot q transpose q dx. But what is q transpose q? It is nothing but the identity. So we have dx dot identity dx, and this is nothing but dx dot dx, which is the length of dx square. So the square lengths are equal, which means the length of dx star is equal to the length of dx if they transform as dx star is equal to q dx. So what is interesting is that two different observers in measuring an infinitesimal vector dx. So two different observers, if the this infinitesimal vector dx star is said to be objective. So this is said to be objective as two different observers arrive at the same conclusion about the length of these two vectors. So the length of a vector is invariant to observers, right? So the length of a vector is invariant to the choice of observers. Two different observers making measurements against different frames of reference will report two different infinitesimal vectors dx star and dx. However, if they are just related by an orthogonal transformation, a proper orthogonal transformation, dx star is equal to q dx, then both of them will report the same length of infinitesimal vectors. Dx star should be equal to the length, dx star should be equal to the length of dx. And such a relationship between vectors in general is called objective vectors. So vectors that obey v star is equal to qv, these are called objective vectors. So this is the condition for objectivity of a vector. So this preserves an invariant of the vector. Similarly, for tensors, the condition is T star is equal to QT Q transpose. So this is an objective tensor. So why is it an object? So why is this condition implying that the tensor is objective? This is because two different observers, O1 and O2, making measurements of a tensor T against some different frames of reference will report the same invariance. Right, you can check. So this transformation is a similarity transformation in matrices. Therefore, the characteristics of the tensor or the matrix has not changed. So in this case, this observers in different frames of reference will report the same invariance if the tensor is objective. So here we have some examples. Is the deformation tensor, is the deformation gradient, is the deformation gradient objective? So the answer is no. We saw that f star is equal to qf, which is not qf q transpose. Therefore, it is not objective. So another name for objectivity is called frame indifference. So it is called frame indifference. Note that it is frame indifference, right? It is not, this is important. There is something else called frame invariant. We'll see that soon. So objectivity is frame indifference, and objective means frame indifferent. So let's look at other tensors. What about the velocity gradient? Velocity gradient. So L is what? L star is, let us say L star. We know that F dot is equal to LF, which means L is equal to F dot F inverse. So L star is equal to F star dot F star inverse. And what is F star dot? It is F star is equal to QF. So it is QF dot QF inverse. So this is Q dot F plus QF dot. And QF inverse is nothing but F inverse Q inverse, and Q inverse is equal to Q transpose. So we have Q dot F inverse Q transpose plus QF dot F inverse Q transpose. So F inverse is nothing but I. So we get Q dot Q transpose plus what is F dot F inverse? F dot F inverse is L plus Q L Q transpose. So see that L star is equal to Q L Q transpose plus some other tensor. So this part is object. This part is frame indifferent. This is you can't say that. This part is what we want. If L is frame indifferent, it should be only QL Q transpose. However, you have a certain tensor sticking to it. We'll see what this tensor is. So if you look at the relationship Q transpose is equal to identity. Now take material time derivative on both sides. We get Q dot Q transpose plus Q transpose dot is equal to 0. This is a constant tensor, which means Q dot Q transpose is equal to minus Q dot transpose. So, so what is this actually? This is actually minus of Q dot Q transpose, the whole transpose. So this is actually a skew symmetric tensor. And this has got a special name, which is called frame spin. Right? So L star is equal to some frame spin, a skew symmetric tensor plus QL Q transpose. Therefore, it is not objective. Next, let us look at the symmetric part of L, which is D. So is this objective? So D is equal to symmetric part of L. So D star is equal to symmetric part of L star. So it is a symmetric part of Q dot Q transpose plus QL Q transpose. This is what we saw. So how do you get the symmetric part? So symmetric part of a tensor A is half of A plus A transpose. And in this case, it is the symmetric part of L star is half of Q dot Q transpose plus Q dot transpose plus Q L Q transpose plus Q L transpose Q transpose. So this sum we already saw, this is equal to 0, which means this is just half of QL Q transpose plus Q L transpose Q transpose, which is Q half of L plus L transpose Q transpose, but half of L plus L transpose is D. So it is QD Q transpose. And what is symmetric part of L star? It is D star. So fortunately, we have D star is equal to QD Q transpose. Therefore, unlike the total velocity gradient, the deformation gradient tensor is objective. Or it is actually frame indifferent. Now, if you look at, so frame indifference is always defined in the spatial coordinates. So the idea of frame indifference is with respect to transformations in the spatial body. Right, because if you look at this example which we just started with, the observations are made in a frame of reference that is fixed to the observer at that particular instant. We don't look at the initial location of these bodies. We don't go and investigate the initial location of the bird or the car. It is at any given snapshot of the system. We look at the concepts of we look at how the tensors and vectors are related. So if you take a material tensor, so if you take material tensors are insensitive or invariant to frame changes. So invariant is not the same as indifferent. Indifference is clearly defined as a certain relationship between the tensors in two different frames of reference. However, invariant with respect to frame change. Invariant means it is exactly the same. Say, for example, if you look at the Green-Lagrange strain tensor, so it is a purely material tensor. It relates the change in length as ds. It relates the infinitesimal length as dx dot cdx. Right. So it does not depend on. It does not depend on any spatial quantity. It takes in a pure material. It takes in two material vectors and returns a scalar. So it's a purely material tensor. C is a purely material tensor. And if you look at C star, which is F star transposed F star. So it is, what is F star? It is QF transpose QF. So this is F transpose QF. And this is nothing but F transpose F, which is C. So purely material tensors are unaffected by a spatial frame change. Of course, that is what we expected. This is entirely defined in the material body referential configuration. And by changing any frames in the spatial coordinate, this is not supposed to change. So C star is equal to C. And it is not frame indifferent. So this is not frame indifferent. It is frame invariant. This frame invariant. It is not objective. It is frame invariant. Okay. Now this is about the kinematic quantities. We can look at stress quantities. Are stresses? How about stresses? So let us look at. So let us say the traction vector is objective. So this is the hypothesis. So T star is equal to Q T. And normals are of course objective. So normal measured against one frame of reference is related to the normal in another rotated frame of reference by this relationship. So if you assume that the traction vector is objective, you have this relation T star is equal to sigma star n star. And T is equal to sigma n. But what is T star? T star is Qt is equal to sigma star Qn, which means T is equal to, take the Q to the other side, you get Q transpose sigma star Qn. Compare these two relationships. T is equal to Q transpose sigma star Qn, and T is also equal to sigma n. So subtract the two, you get Q transpose for arbitrary normals, you get Q transpose sigma star Q minus sigma is equal to 0, which implies by a certain rearrangement, you get sigma star is equal to Q sigma Q transpose. So the Cauchy stress tensor is objective. The Cauchy stress tensor is objective. What about the rate? What about the material? What about the material time derivatives of sigma? Material time derivative of sigma. There is no. So you know sigma dot is defined as d by dt of sigma. Now let us define sigma star as sigma star dot. Let us look at this quantity. Right, sigma star is nothing but q sigma q transpose, the whole dot. So use the product rule. This results in q dot sigma q transpose plus q sigma dot q transpose plus q sigma q transpose dot. So this is actually q sigma dot q transpose plus a certain tensor, which is q dot sigma q transpose plus q sigma dot q transpose dot. So if the rate is just if only these two are there, then the rate of Cauchy stress, the time derivative of the material time derivative of Cauchy stress would have been objective. But unfortunately, we have a certain term added to it, which is not zero. Therefore, the material time derivative of the Cauchy stress. So the material time derivative of Cauchy stress is not objective. Right. So what do we do? Because if it is not objective, then it cannot enter a constitutive relation. Okay, by the way, I didn't say the restrictions on the constitutive relationships, right? We just we'll get to that now, right? Because that is important. So by common sense or from so this you might have seen in the lecture. So there are certain fundamental relationships. Physically, we expect certain fundamental relationships to be satisfied while deriving a constitutive relationship. So the first one is principle of determinism. The first one is principle of determinism. Principle of determinism or causality. So the principle of determinism states that only past events can influence the present, right? So for example, the stress at a given point in the material can only depend on the history of strains at, so it is a function only of the history of the strains from, so it is let me just put D. So in words first, the principle of determinism states that the present state, the present state is related, depends only on the events in the past, right? So you cannot have so if suppose there is a function that is relating the stress to some strain, it can only depend on strains from time t equal to minus infinity to, so say it can depend on time, but this can only be from this time dependence is only from, say, t is minus infinity to the current time, right? So this can only depend on the strain at time t stars, where t star is everything from minus infinity to the current time. So suppose the stress at the current time instant t depends only on this the strains from strains in the past, right? So this is the principle of determinism. The stress at the current instant cannot depend on the strain in the future. So you cannot have a t star greater than t that determines the stress at the time t. So this is one physical idea. You don't expect events to be related, the current events to be depending on the events in the future. That is one thing. The second idea, as you see in the presentation, in Sir's presentation, if you look at his notes, it is the principle of locality. So the principle of locality states that the stress at a given point depends only on the strains and the deformation at that given point. So the stress at a point x comma t depends only on the deformation. It's a function only of the deformation at that point, and you can so you cannot have non-locality. So the stress at a given point cannot depend on the strain at some other point. So this is another principle of locality, and this is not universally accepted, as Sir said. For certain applications, there are non-local material models which help. Right? For structured media, there is something called non-local material models. Then the constitutive relationship is expected to obey the second law. So second law, as you saw, is an inequality constraint. It is an inequality constraint. Second law of thermodynamics, of course. We have an inequality constraint, and that should be satisfied. So basically, the entropy of an isolated system cannot decrease. So n dot has to be greater than or equal to 0. So this has to be satisfied. Whatever constitutive relationship we have has to obey the second law of thermodynamics. And finally, it has to be objective. The constitutive relationship. So objective quantities have to get into the constitutive relationship. Not only that, the functional form itself has to be objective. So as observed by two different observers, so the constitutive relationship has to be objective. So it should be observer invariant and form invariant. So this is absolutely required. If you have some functional form, they have to be invariant to who is making the observations in which frame of reference. And the form of the constitutive relationship should also not change. But in addition, we have something called material objectivity or material frame indifference. Again, this is not a universally accepted concept, but most of the constitutive relationship that we have in practice are material frame indifferent. So material frame indifference states that this this is with respect to transformation. Observer and form invariants are with respect to transformations in the spatial coordinate. So these are transformations in the spatial coordinate, in the spatial body, right? You superimpose a rigid motion Q on the spatial body, and then you say that the concept relationship is indifferent to superimposed rigid body motions. But what is even more restrictive is material frame indifference. So material frame indifference, that you superimpose a rigidity on the body, right? You superimpose a rigid body motion on the material body. So the transformation is yeah. So you have a material body, and then uh, you apply a rigid motion onto the material body, and then whatever relationship we have, say sigma is equal to f of epsilon, that should be invariant. That should be indifferent to uh, superimposed rigid bodies motions on the material body. So these are four fundamental restrictions on the causal relationship, that it should depend only on the past, not the future. It has to depend only at the current point. The stress at a current point is a function only of the strains and the temperature at that point. Then we have the second law of thermodynamics, which is an inequality constraint. The constitutive relationship should be such that for arbitrary processes, the entropy of an isolated system always increases or remains constant and does not decrease. And we have the objectivity constraint, or objectivity constraint is that the constitutive relationship is indifferent to spatial observer, spatial frame of reference. Not only that, we also have a restrictive material frame indifference axiom, which says that the constitutive relationship is indifferent to changes in the material frame of reference, not the spatial. So this is more restrictive. So this is more restrictive. So based on these, we have a variety of different materials, different types of materials. So they are, so first one is what we call simple materials. So by simple material, uh, so a simple material is something that has the constitutive relationship itself depends only on the current deformation. The constitutive relationship. Wait a minute. So it is, should be careful. It's not the relationship. The constitutive behavior depends only on the current state. So if you have a function sigma is equal to f of, say, f or d, this f itself is not a function of time. So, but this actually this can depend on f. So f and f dot actually. So this can depend on f and f dot. From time t is equal to minus infinity to the current time. Right? So the stress response at the current time can depend only on the constant. It's some function of the deformation gradient and the rate of deformation gradient at all times from minus infinity to, so T star is going from minus infinity to the current time. So this is the definition of a simple material. The response, the stress response or the constitutive behavior depends on a fixed function. The function itself is not a function of time. The relationship itself is not a function of time, but it can depend on everything from minus infinity, which is like anything back in the history to the current point. So this is the definition of a simple material, and we have some. We can further go ahead and define what is an elastic material. An elastic material is a material without memory. Material without memory. So essentially, the response is dependent only on, is a function only of the deformation at the current instant and gradient of the deformation at the current instant. Sorry, the time derivative of the deformation at the current instant. So it does not depend on the history of the deformation gradient. So a simple elastic material is one in which this relationship itself does not depend on time, and it is also it doesn't have memory. So a simple elastic material is uh, a material without memory. That is, the response depends only on the current state of deformation. And the constitutive relations themselves do not depend on time. Right. So, so this was actually covered in the course content. So we can, and further we can have different types of material symmetry. You have material symmetry. So this will come up in the next week's content, right? So we can have different types of material symmetry, isotropic, transversely isotropic, etc. And they have certain other restrictions on the constitutive relationships. And then you have hyperelasticity, which is the only kind of materials that will be considered in this course, right? So hyperelasticity is the stresses are derivable. Hyperelastic material is one. Is an elastic material in which the stresses are derivable from a stored energy function or a strain energy function. Stored energy or a strain energy function. as follows. So say S is equal to del psi by del E. Right. So if the second pure Kirchhoff stress is derivable as the derivative of a strain energy function with respect to the green Lagrange state, then this defines a hyperelastic material. So it's also known as a green hyperelastic material, right? So that is fine. So that psi is also known as the stored energy function or the elastic potential. Okay, so then we get to the concept of so these are right. So these are some ideas relating. So what is to be remembered is that constitutive relations have to obey certain requirements. One is the determinism, which is universal. It cannot have things that depend on the future. Locality, that the stress at a point depends only on the strains deformation at the current at that point and not any other points. It has to obey the second law of thermodynamics, and this is checked by a procedure called Coleman-Knoll procedure. Coleman-Knoll procedure. This is from 1963. And there's also a condition of material frame indifference that has to be respected. These are for any constitutive model, but based on the type of material, we can have simple materials wherein the constitutive relationship depends only on the current state. And we have an elastic material, which is memoryless material, does not depend on the deformation in the past. So a simple elastic material is a one which doesn't have memory, and also the relations do not depend on time. Then we have a hyperelastic material, which is an elastic material in which stresses are derivable from a stored energy function or a strain energy function psi. Okay, so these are some basic ideas. So one, as we saw, one requirement is that the constitutive relationship has to be frame indifferent, or it has to be objective. Two different observers should not disagree upon the constitutive relationship of a material, because the constitutive relationship is something fundamental to the material. It should not depend on which observer is reporting it. So two different observers have to have some consistency in reporting the constitutive relationships. So we saw that the rate of getting back to it, the material time derivative of the stress tensor, the Cauchy stress tensor, we said it is not objective. So what do? We need to come up with objective stress measures. We need to get with objective stress measures. Objective stress rate measures. So one idea is Truesdell stress rate. So there are many of these, and sir would have gone through this in the last week's lectures. So one is the Truesdell stress rate. It is defined as the Piola transform of the material time derivative of the second Piola-Kirchhoff stress tensor S. So we'll see what it is. So we have it is defined. It is denoted by the small circle above sigma. It is defined as the Piola transform. So it is J inverse of so the Piola transform is nothing but it is a scaled Piola transform is nothing but a scaled push forward, right? So when we push it forward, we use the scale. So it's like uh, the Kirchhoff stress tensor. The Kirchhoff stress tensor is the scaled version of the Cauchy stress, right? So similarly, the Piola transform is nothing but a scaled push forward. So you have J inverse, which is a scaling factor with a push forward operation on the material time derivative of S. So it is S dot. So this is basically J inverse. Why is there a there is some connection issue? Yeah, so it is J inverse. The push forward operation we use for the push forward operation we use F, right? We use just a minute. So we have so J. So we have a J inverse and J and this two gets cancelled. Let me just check. Yeah. So the push forward of this tensor is nothing but F S dot F transpose. So remember, S takes in a material vector and returns another material vector, right? So S takes in the normal in the deformed configuration and it returns the pullback of the traction vector. So it returns F inverse T. So it returns a material vector. So F takes a material vector and returns a spatial vector. So F inverse takes a spatial vector, which is the traction T naught, and returns a material vector, which is F inverse T naught. So if you have to transform this stress, you need to get a quantity which takes in a material vector, which takes in a spatial vector and return a spatial vector. So N naught transforms as N naught is nothing but Q transpose. Sorry, there's no Q here. It is so okay. So that's fine. We'll so this is a push forward of S dot. Right now, S dot, you can write this as S is what? S is J sigma. S is J F inverse sigma F inverse transpose. And you can show that S dot is you can do it as an exercise. J dot is S dot is J dot F inverse sigma F inverse transpose. Just apply product rule plus J F dot inverse sigma F inverse transpose plus J F inverse sigma dot F inverse transpose plus J F inverse sigma F inverse transpose dot. So this is straightforward. I'm just applying the product rule. What is J dot? We need to see what J dot is. So J dot is divergence of, it's the trace of L, which is the same as the divergence of the velocity field times J. So this relationship is this is a known relationship, and this is also equal to the divergence of V times J. So substitute this, you get S dot is equal to the trace of. So what is the trace of L? So trace of L is L has a symmetric part and an anti-symmetric part. So the spin tensor and the rate of deformation tensor. But the spin tensor is anti-symmetric. Therefore, it has trace 0. So you get, so the trace of W and the trace of W transpose have to be the same. But if you take trace on both sides, you get a minus. So which means you get the trace of an anti-symmetric skewed symmetric tensor is 0. So the trace of L is nothing but it is trace of D. So this is basically this is trace of D, J, F inverse F inverse transpose plus the other two terms, other three terms are unchanged. So plus you have a J. What is the next term? Yeah, we have an f dot, f inverse dot. So what is f inverse dot? It is so let's do that. What is f inverse dot? So start with f. F inverse is equal to I. Differentiate it. You get f dot f inverse plus f inverse dot is equal to 0. Therefore, f inverse dot is equal to minus f dot f inverse, and therefore f inverse dot is equal to minus f inverse f dot f inverse. But what is f dot? It is LF. So it is minus f inverse LF f inverse. So f inverse is I. So this is nothing but minus f inverse L. So f inverse dot, you can put it as minus f inverse L sigma f inverse transpose plus what are the other two terms? We have J f inverse sigma dot f inverse transpose plus you have J f inverse sigma f inverse uh, dot transpose. So dot and transpose can be swapped. So you get an L transpose. So you just get a transpose of this, right? So you get an L transpose f inverse transpose. So this is the expression for S dot. But what is sigma? How do we define this Truesdale stress rate? It is a scaled version. It is a Piola transform of uh, f, the push forward of the material time derivative of this tensor S. So let us proceed further. So you are using f to push it forward. So the first term you multiply f and f transpose, these two will vanish. So you get trace of d. So sigma dot is equal to trace of d. You have a j inverse. So j inverse and j gets cancelled. F cancels with f inverse. F inverse transpose cancelled with f transpose. So you get a trace of dj plus, what about the second term? J will get cancelled. F inverse, F transpose inverse will get cancelled. You get a minus L sigma. And from the third term, J F inverse transpose goes away. You get a sigma dot. Plus what from the last term you get. So there's a minus here, right? There's a minus here. F inverse J goes away. And F inverse transpose goes away. So you get a plus, a minus L sigma, minus sigma. You have a minus L transpose. So let me rearrange it. Again, it is sigma dot minus L sigma minus sigma L transpose plus trace of d j. So this is called the Truesdale stress rate, and this is the scaled uh, this is the scaled push forward of S. So it can also be represented in terms of the Kirchhoff stress rate. It is nothing but the material time derivative of the Kirchhoff stress minus L times the Kirchhoff stress minus this Kirchhoff stress L transpose. So this is in terms of the Cauchy stress, and this is in terms of the Kirchhoff stress. So this one is objective. So we can check that this rate is objective. That's a problem we have. No, oh yeah, okay. Yeah, you can easily show that this stress is an objective rate. Why is it objective? Because this is the Lie derivative of it's a scaled Lie derivative of the sigma. So we can show that this is objective. How do we do that? We can make the look at what is sigma dot star. this is nothing but trace of D star, J star minus L star, sigma star minus sigma star, L star transpose minus sigma dot star. So the trace of a tensor is invariant. So this is nothing but so D star is Q D Q transpose, and the trace is unaffected by the orthogonal transformation Q. So this is just trace of D. J is a scalar, so J star is equal to J. Scalars are unaffected by frame rotations. L star is what? L star is Q dot Q transpose plus QL Q transpose. What about sigma star? Sigma star is Q sigma Q transpose. And this from the third term we get Q sigma Q transpose Q dot Q transpose plus Q transpose minus sigma dot star. So what it is, that is, let us just have it as it is not expanded, minus sigma dot. Sorry, this is plus. Sorry, this is plus. Now make this. So this can be summed up. So you get multiply with the first term, you get a Q dot sigma Q transpose. So we get sigma star dot. So this is the true stress rate in a different reference frame is nothing but trace of D J, right? So this is a scalar. This is sorry, there's something that is off. Yeah, sorry, it's not J. It is J gets cancelled. F inverse transpose gets cancelled. So it's trace of D sigma, not J. Sorry about it. This is sigma. This is sigma star. So this is sigma star. So let me put this as sigma star. Sorry about it. So here we have a sigma star. So this first term gives Q dot sigma Q transpose. And this is Q L sigma Q transpose. So Q transpose Q gets cancelled. So plus Q L sigma Q transpose. And this entire thing is there's a minus sign. So this is with a minus sign. Then the second term, what do we have? So this multiplies with the first term, you get Q sigma. So we have to transpose it first. So when we transpose it, this becomes Q dot transpose. So this will become Q sigma. You have a Q transpose Q, so it's Q dot transpose plus from the second term you get so transpose of this is Q L transpose Q transpose. So Q transpose Q gets cancelled, so you get Q sigma L transpose. Okay. And plus you have the last term, which is sigma star dot. Now rearrange the terms. So you get sigma, you can sigma star is nothing but Q sigma Q transpose. So this trace of D can be inside. So you get a Q trace of D sigma Q transpose. Take all the terms with the Q transpose to one side. So you get a minus Q L sigma Q transpose minus Q sigma L transpose Q transpose. Plus collect the other terms. So you get a sigma dot star minus Q dot sigma Q transpose minus Q sigma Q dot transpose. So from the first set of terms, you can take Q commonly out, and what you get, trace of T sigma minus L sigma minus sigma L transpose, and that is nothing but the Truesdell stress rate, right? So that's nothing but the Truesdell stress rate minus something. So that is the Truesdell stress. So these are the terms in the Truesdell stress rate minus something else. So it is the Truesdell stress rate minus sigma dot. Okay, have it as it is. From the second term, what do we see? This is and we have a Q transpose here. From the second term, we have a sigma dot star. But what is sigma star dot? So we saw that it is not objective. Yeah. So sigma star dot is Q sigma dot Q transpose plus something else, right? So we will write it as it is, which means sigma star dot. So these two are the terms appearing there, right? It's Q dot sigma Q transpose plus Q sigma dot Q transpose dot. This is on the left hand side. So you see, so Q dot sigma Q transpose and Q sigma dot Q transpose dot. So this is basically Q sigma dot Q transpose. And there's a Q sigma dot Q transpose here. These two gets cancelled. And we are left with Q sigma circle Q transpose. Therefore, the Truesdell stress rate is objective. Okay. So yeah, so this proves the objectivity of a certain stress rate. So similarly, there are other stress rates which we couldn't cover last time. I hope this time we can. So there is something called the Oldroyd stress rate, which doesn't have the trace of D times sigma. So we have an Oldroyd stress rate, which is defined as sigma with a filled circle is just sigma dot minus L sigma minus sigma L transpose. You don't need to memorize this stuff. It is just that they are used in constitutive relationships. Then if we do the pullback and push forward, so we define the Truesdell stress rate as J inverse of push forward of S dot, right? We can do and in this push forward we used F and F transpose. We can also do the same push forward with F inverse transpose and F inverse. So F inverse pulls it back and F inverse transpose pushes it forward. So by doing this, or rather, it's actually F inverse transpose and F transpose. Yeah. So using this, we can arrive at another stress rate called the convective stress rate. So this is the convective stress rate. So this is the rate of stress with respect to a frame of reference that is convecting with the coordinate system. So this will result in, so this is denoted by sigma diamond, that is given as sigma dot plus L transpose sigma plus sigma L. Then these are actual, so these are actual stress rates. Or you can show that all of these, the Truesdell stress rate, the Oldroyd stress rate, the convective stress rate, they are all frame indifferent. And there are also other stress rates called the Green-Nagdi stress rate. Nagdi stress rate, where instead of using the full deformation, you use R, right? Instead of taking F for the pullback and push forward, you use R. So that results in the Green-Nagdi stress rate. You can refer to the lecture notes. And we also have something called the Yeoman stress rate. In the Yeoman stress rate, we approximate R dot R transpose by the frame spin W. No, sorry, it's by not the frame spin, by the skew symmetric part of the deformation gradient, deformation rate of skew symmetric part of the velocity gradient, which is W. So these two give rise to other stress rates. So here is a problem from this Borneo and Wood. So the Yeoman stress rate is defined as sigma the rate minus W sigma plus sigma W. So this proved directly that the Yeoman stress rate is an objective tensor. You can do that. So look at sigma dot sigma star triangle. So this is nothing but sigma star dot minus W star sigma star plus sigma star W star. Proceed in the same way as we did for the true stress rate. So what is sigma star dot? Sigma star dot is Q dot sigma Q transpose plus Q sigma dot Q transpose plus Q sigma Q transpose dot. What about W? W, it is defined as Q dot Q transpose. So W star is sorry. So W itself is we'll get to this, right? So let me. Yeah, so W is the skew symmetric part of L. So W star is the skew symmetric part of L star. But what is L star? L star is Q dot Q transpose plus QL Q transpose. So W star is basically this. The skew symmetric part of a skew symmetric tensor is the entire tensor Q dot Q transpose plus QW Q transpose. Okay, so this is the relationship. So W star is Q dot Q transpose plus QW Q transpose. So in place of W star, substitute that. So you get a minus Q dot Q transpose plus QW Q transpose. Sigma star is Q sigma Q transpose plus Q dot Q transpose. So sorry, Q sigma Q transpose with W star is Q dot Q transpose plus QW Q transpose. So add them all up, we get so here Q transpose and Q gets cancelled, you get a minus Q dot sigma Q transpose. So let me write it down. So sigma star, the Yeoman stress rate of sigma star is Q dot sigma Q transpose plus Q sigma dot Q transpose plus Q sigma Q transpose dot minus the first term is Q dot sigma Q transpose. What is the second term? Second term is Q W sigma Q transpose minus Q W sigma Q transpose. And what is from this? You get a Q sigma Q transpose Q dot Q transpose. So you get a plus Q sigma Q transpose Q dot Q transpose. And the next one is Q sigma W Q transpose plus Q sigma W Q transpose. Now, what is Q transpose Q dot? So Q transpose. So look at Q transpose Q is equal to I. Differentiate, you get Q transpose dot Q plus which means Q transpose Q dot is equal to minus Q dot transpose Q. So plug this into this part. So in place of Q transpose Q dot, you can substitute with this. So it becomes, so this term becomes, this term is equal to Q sigma minus Q, there's a minus sign, Q dot transpose. So Q transpose is again 1. So this one cancels with this one, Q sigma Q dot transpose. This one cancels with this term, and we are left with sigma star. This one is equal to Q. So all the terms have Q transpose. And if you remove it, you get sigma minus W sigma plus sigma W Q transpose. So which is basically, therefore the Yeoman stress rate is also objective. Then we have another problem. So prove that dx1 and dx2 are arbitrary if they are arbitrarily elemental vectors moving with the body. Then prove this relationship, right? So in this relationship, we have the convective stress rate coming into picture. We can do that. So dx1, so d by dt of x1 dot sigma dx2. This is what we have. Use the product rule. So we get this is, or before the product rule, let us take it back to the reference, right? So this is dx1 rather is f dx1 dot with sigma f dx2. So using the property of transpose, you can write it as d by dt of dx1 dot f transpose sigma f dx2. Note that these two are material vectors. They cannot change with time. So you can take the derivative to inside. So you get dx1 dot d by dt of f transpose sigma f dot dx2. So if you recall, what is f transpose sigma f? Or let's just do it, right? So we have, let us call this quantity as some, say some 1, right? 1 is d by dt of f transpose sigma f. So note that f is a sigma is a spatial tensor. It takes in a spatial normal and returns a spatial traction vector. F is going to pull it back. So the transformation f transpose sigma f pulls sigma back to the reference configuration. So this will actually take a material vector and return a material vector. So f acts on a material vector, returns a spatial. Sigma takes a spatial, returns a spatial. F transpose takes a spatial and returns a material. So this is the time derivative of a material quantity. So it's a Lie derivative. It is a Lie derivative. So I use the product rule. So you get, it is f dot transpose sigma f plus f transpose sigma dot f plus f transpose sigma f dot, and use the relation f dot is equal to LF. What do we get? So 1 is equal to LF transpose sigma f plus f transpose sigma dot f plus f transpose sigma LF. Now proceed further. We get f transpose L transpose sigma F plus F transpose sigma dot F plus F transpose sigma LF. Now take F transpose F common from all. So you get an F transpose L transpose sigma plus sigma dot plus sigma L times F. But what is this entire thing? This is the convective stress rate. So this is F transpose sigma diamond F. Now substitute this back into this expression. So we get d by dt of dx1 dot sigma dx2 is nothing but d capital X1 dot F transpose the convective stress derivative, convective stress F dx2. Now, if you look at what this is, so again, you can use the principle of property of transpose and take this F back. So you get this is d by dt of dx1 dot sigma dx2 is nothing but F dx1 dot the convective stress rate F dx2. So F dx1 is nothing but dx1 dot convective stress rate dx2. So this completes the proof. Right. So this completes the proof. This is what we wanted to show here. Okay, so this is all about stress rates, objective stress rates. Then finally, let us yeah, we have a little bit of time. I'll just finish the last concept, which is the elasticity tensor. So the elasticity tensor in the material elasticity tensor is defined as follows. It is defined as so material elasticity is at C, right? Let me use a bold C. It is defined as the relationship between the directional derivative of S in the direction of the deformation in the direction of displacement is nothing but C double dot with D E U. This is the relationship between this tensor, which relates the directional derivative of S in the direction U and E in the direction U, is the material elasticity tensor. We also have a, so if you look at the, and this is a Lagrangian quantity, you also have a spatial elasticity tensor or an Eulerian elasticity tensor. And that is the directional derivative, but in the direction of the velocities, right? So it is so these two are note that these two are this S and E are material tensors. They are material tensors and work conjugate with respect to the undeformed volume. They are work conjugate material tensors. Therefore, since S and E are material tensors, the elasticity tensor bold C is also a material tensor. But you can also have a spatial elasticity tensor, which relates the rate of denoted by small c. It relates the rate of sigma with the velocity gradient. So this d is the rate of deformation, the symmetric part of velocity gradient. So this is the rate of deformation tensor, and stress rate. This is the true stress rate. So this is obtained by taking the directional derivative of these quantities in the direction of velocity, and then we carry out a push forward operation. So this is the spatial elasticity tensor. This is a material elasticity tensor. So in this week's assignment, there is one question based on this topic. So I'll solve something similar to that, but not the same. So for a Steinway and Kirchhoff material, they have given the strain energy potential and the expression for the second Piola-Kirchhoff stress tensor is to be derived. And they're also asking what is the expression for the Kirchhoff stress tensor and the material elasticity tensor, right? So this. Okay, yeah, but yeah. Okay, so this will do it right now. So I'm not supposed to solve the same problem, but instead of the Steinway and Kirchhoff material, I can use a different strain energy potential. So let us start with. Let me start with this, the neo-Hookean material, right? So just a minute. Hyperelastic. Yeah. So here it is. So let us start with the. So I will. So this the idea of the questions 5, 6, 7, 8 of the assignment is that given a potential, are we able to derive the expressions for the stresses and the elasticity tensor? So we'll do it right now, not for the same material that is for a Steinway and Kirchhoff material, but I will do it for a neo-Hookean, not neo-Hookean. It is a modified Steinway and Kirchhoff material. So it's called a Henke material, right? So let us start with, yeah. So there is the stored energy function for a material is given. So this is a problem. The stored energy function for a material is given as, and this is from Professor C.S. Jogues' Continuum Mechanics book, chapter 4, chapter on nonlinear elasticity. So the stored energy function for a material is given as lambda by 2. Lambda is a constant. Log of lambda 1 plus log of lambda 2 plus log of lambda 3 plus mu times log of lambda 1 square plus log of lambda 2 square. So this is the log of lambda the whole square plus log of lambda. So this you can, so lambda, so here lambda 1, lambda 2, lambda 3 are the principal stretches. Principal stretches. So given that principal stretches, as you know, they are the eigenvalues of C. Eigenvalues of U or P. Both of them have the same eigenvalues. Now, can we determine what is the so this in another form? So you see that log of lambda 1 plus log of lambda 2 plus log of lambda 3. Using the properties of logarithm, it is nothing but log of lambda 1, lambda 2, lambda 3. But what is lambda 1, lambda 2, lambda 3? It is the product of eigenvalues of U. So this is nothing but, so this one is actually square. So this is basically, yeah, so this, the product of eigenvalues, as you know, is the determinant of U. Now, we want the constituent relationship between S and C, right? So we can write this determinant of U as square root of determinant of C, because U is equal to square, U square is equal to C. So determinant of U, the whole square is equal to determinant of C. Therefore, determinant of U is square root of C. So log of determinant of U is nothing but half of log of determinant of C. So the first term is actually W tilde is equal to lambda by 2 log of determinant of C divided by 2, the whole square. Plus, what is the second term? Second term, we have logs, log of lambda 1 square, log of lambda 2 square, log of lambda 3 square. But what is this? This is basically log U double dot with log U. So the strain energy potential can be given as log U plus mu times log U double dot with log U. So start with this expression for the strain energy potential, which is W is given as lambda by 8 log of determinant of C, the whole square, plus mu times log U double dot with log U. Now again, this log U can be written as log C is, so C is equal to U square. So log C is nothing but 2 log U. So this can be, so the to derive S is nothing but half of, the derivative of W with respect to C. So S and E are work conjugate. So this is the hyperelastic relationship. So for materials for which S is derived as the time derivative, sorry, it's a 2 here. This is the definition of a hyperelastic material, but E is equal to half C minus I. Therefore, dou by dou E is nothing but 2 times dou W by dou C. Now do this derivative. So if you look at the first term alone, so just a minute. So S in this case is given as 2 times lambda by 8. So lambda is a constant. So we have to differentiate this. This results in 2 times log of determinant of C. Use the chain rule. So this is a tensor. So sorry, this is a scalar. Then we have log of determinant of C. So that becomes divided by determinant of C. And then you have dou determinant of C with respect to C. So the first term results in this plus plus you have a mu by 4 log C double dot with log C. So proceed further. The first term gives so if you look at this, you have this relationship. So the derivative of determinant of a tensor divided by with respect to the tensor itself is nothing but the cofactor of the tensor. So if you want to see how it comes, you can look at the material time derivative of the determinant. So use this expression, and what we get is this. So we get S is equal to the first term. So this becomes cofactor of C. Let me use a different color. This term becomes cofactor of C. But also, so S is equal to, you get a lambda 2 gets cancelled, you get a lambda by 2. You have log of determinant of C divided by the determinant of C multiplied by cofactor of C. And in the second term, what do we have? We have log C, inner product with log C. So plus you have a lambda by 4. So the inner product is symmetric. So it is just 2 times log C. You get a 2 times log C inner product with the derivative of log C with respect to C, which is C inverse multiplied by dou C with respect to C. So C with respect to C is the fourth order identity. So it is just C inverse. Now look at the first term and look at this. You have a cofactor of C divided by determinant of C. So you have lambda by 2 log of determinant of C multiply cofactor of C divided by determinant of C plus lambda by 2 log of C. Sorry, this is not lambda by 2. This is mu. Sorry about this. You have a mu here, and this becomes mu times log C inner product. So we have a log U inner product with log U. We have a mu log U inner product with log U. And this U can be written as C is equal to U square. C is equal to U square. So log C is equal to 2 log U. So this second term is nothing but mu by 4 log C double dot with log C. So this is basically mu by 4 Cij Cij. Now we want to get dou by dou CKL mu by 4 Cij Cij. Use the product rule. So this will give us mu by 4 dou by dou CKL of dou by dou CKL of Cij. You have a Cij outside plus you have a mu by 4 dou Cij by dou CKL Cij. So this is equal to mu by 2 dou Cij by dou CKL Cij. But what is dou Cij by dou CKL? It is mu by 2. So this is equal only here. So Cij and CKL are symmetric tensors. So if I is equal to K and J equal to L, we get one term, which is delta Ik just a minute. So we had lambda by 2 determinant of C. Yeah. So it's a delta Ik delta JL plus delta. So whether if J is equal to K and I is equal to L also, we get a non-zero thing. So it's delta IL delta Kj multiplying Cij. So in place of I and J, you can do this replacement. So you get a mu by 2. In place of I, put K. So you get a CKL plus CLK. But CKL is equal to CLK since C is a symmetric tensor. So it is basically mu CKL. So therefore, the derivative of this, the second term with respect to C is nothing but where is it? So okay, sorry, there's a log. There's a log here. So everywhere you get a divided by CKL. Sorry about it. Okay, let's do it step by step. So S is equal to this. The first part is clear. The first part is only so much. We get a lambda by 2, some lambda by 2. So in the first part, we get a lambda by 2 log of determinant of C multiplied with cofactor of C divided by determinant of C. So this is the first part. Plus we have a mu by 4. We have a 2 times mu by 4. So the 2 comes from, so the differentiation with respect to C. We have a 2 times dou W by dou C. So mu dou by dou C of log U inner product with log. Right? So let us take the first term. We have a cofactor of C determinant divided by determinant of C. But if you remember, C inverse is what? C inverse is 1 by determinant of C, cofactor of C transpose, right? So cofactor of C is determinant divided by determinant of C is nothing but C inverse transpose. But C is symmetric, so C inverse is symmetric. So this is nothing but C inverse. So this is nothing but C inverse. So in the first term, I can replace this entire thing by C inverse. Now look at the second term. The second term, what do I have? I have a mu by 2 dou by dou C of log U inner product log U, but log U inner product log U is 1 by 4. Sorry, so this is already log C inner product log C because I have made this mu by 4 here. So this is log C inner product with log C. And this is nothing but mu by 2 dou by dou C of log Cij log Cij. This is symmetric, so you get a mu, use the chain rule, you get a log Cij dou by dou C of log Cij. What is log dou by dou C of log Cij? It is mu log Cij. Use the product rule, use the chain rule, so you get 1 by CKL dou CKL divided by dou Cij. So this is, yeah, so this is with respect to, say, KL. So here I cannot use KL. I have to use some other. So this is dou CPQ, PQ, KL. Proceed further, you get mu yeah, so this is Ij. So this has to be Ij. Sorry. So log Cij derivative is nothing PQ So this will result in mu log C delta. This will be an identity C inverse in the tensor notation. So the second term is, this entire thing is mu log C inverse. Now finally, so this has a C inverse, this has got a C inverse. Put them together, so you get S is equal to lambda by 2 log of determinant of C. This is a scalar multiplied with identity plus mu log of C, this entire thing multiplied by C inverse. So this is the expression for stress given the strain energy potential W. So this last part I'll clarify. This part I'll clarify later on. But the procedure, the stress potential, the stress strain energy function given in the assignment is much simpler. We don't have the eigenvalues involved directly, so that is supposed to be simpler. I think you can do the same. So yeah, way past time. I'll end the session here. In case you have any questions, you can ask. Okay, I'll stop the recording, and thank you for attending.